our course we had been doing string theory in a flat space-time metric, but to understand string theory as a theory of gravity, there should be some restrictions on the space-time that should allow geometries of space-time that should come out of the string theory. In the same way, the Einstein theory of relativity restricts the space of allowed manifolds in a certain way. So for that it is important that we study the string theory in a curved background, curved space-time background, and the most trivial generalization for that is to include a curved metric for space-time in the Polyakov action, so that the action becomes where G mu x is the space-time metric, and therefore it depends on the space-time coordinates capital X. Okay, but at this point, like in our analysis of the spectrum of string theory, we had found out some massless spin to objects, massless spin to states, which we had tried to relate to gravitons, and but from in general relativity we have an understanding of what gravitons are, and those are the fluctuations around flat metric for So this is what we usually identify with gravitons in GR. So it should be the case that these fluctuations are somehow related to the massless states of the string theory that we had computed while computing the spectrum earlier. So
capital G mu is fixed, right? It's not like Einstein theory where it's
for now it is some function of x.
It's fixed, but it will turn out to be an equation of it. So it is in the end like Einstein.
But apparently there is no reason for there to be some constraints on this.
A priori there are no constraints for, but since so the constraints that will come out at the end of today's class are because we will demand whatever action we write down to be while invariant, and which was important throughout the analysis of string theory. So just if we demand that whatever this theory on world sheet, field theory on the world sheet be while invariant, that will impose constraints on G mu, and that as it will turn out to be will be the Einstein equation.
Right. And just one more thing to say. Suppose you take this capital G, maybe you're going to say that. You take this capital G and make it eta plus h.
Yeah.
And you take e to the power minus s. And then you expand that in small h. What do you get? So I'll try that.
I was
You're going to do that.
So if so just to relate the two states in the massless states in the closed string theory and the G mu that we understand as graviton classically, what we can do is write the partition function and expand we can expand G mu around the flat metric and treat these perturbatively. So what we get is some 1 minus d2 sigma root G del alpha x mu del beta x mu h mu G alpha. Okay, and now this is what was the vertex operator for the massless string states that we had computed earlier.
H mu of x, let's call it.
Yeah.
Now the actual vertex operator we computed for a particular form of this h mu.
Which is some polarization constant times e to the power I p dot.
Exactly. And so this is like bringing down, as you're saying, a vertex vector But we saw that in string theory you can't bring down any old vertex point. It has to be on-shell. Right? So that on-shelness is the Fourier space statement of linearized Einstein equations. You see, that H mu nu could not have been anything. It had to be a linear combination of the kinds of things Prandtl has written down. Because this is a vertex operator, right? You write it down with an arbitrary A of P times this. One vertex operator. But those vertex operators all had to obey a Marshall condition. Marshall condition was some condition on the polarization and that P squared was equal to 0. But those two conditions are simply, in this Lorentz case, are simply the linearized Einstein equation. So we've already seen that if you take what Prandtl has done and expand to linear order in H, what we get is insertions of vertex operators, but we've already seen that we were not allowed to insert arbitrary vertex operators, only allowed to insert them on shell. So this is already an indication that something should go wrong if we try to put an arbitrary G and don't have it satisfy the equation. Because at least in the case where it's linear, good things only happen when the linearized fluctuation obeys the Einstein equation. So already we see that something will go wrong if G is arbitrary and not obeying an equation. Right.
So now we all this was not the only possible state that we had at massless state that we had in string theory. There were other states which were in the antisymmetric. So here for this to be the graviton, and since it's coming from the metric, we know this polarization vector is symmetric here. So we could very well equivalently ask that the other states that we had obtained in the string theory, which were in the antisymmetric representation and one scalar, could that be incorporated in our classical action? And if we do the similar exponentiation for those states, we find that we can add two terms to the this action, and that would be the most general renormalization action on the world shape that is allowed. So those additions to the action are simply an addition of antisymmetric field where this is antisymmetric in mu nu indices, and another addition which comes due to the scalar, which is d2 sigma r to phi of x. Okay, and so this is the most general action which obeys diff invariance on the world shape, and which is also covariant in the space-time coordinates. But there's one important thing to notice is that this part of the action is not while invariant, and that is because this field phi has weight 1. So under while transformation, this whole action picks up a factor corresponding to that of one weight 1 fields. Okay, so as it will turn out later that alpha prime is some loop counting parameter for our, will turn out to be the loop counting parameter in our analysis, and we have introduced this part of the action at one lower order of alpha prime. Therefore, the while invariance, while anomaly that appears due to this part of the action will appear at the same level as the while anomaly which appears from these two parts of the action at order alpha prime to the power 0, and they will combine together to give a while invariant answer. Okay.
Sorry, why is phi of weight 1?
Phi is of weight 1 because this is the trace part of, so this is essentially the created out of this state, right? Phi J bar acting on 0. And this state, the weight of this state in the worldsheet theory is 1.
I see. So you're saying that it's because conformal weight is 1,
Yes.
but it was a worldsheet scalar. So under diffeomorphisms it didn't transform. So all of the conformal weight came from the binary.
Yes.
So the factors of alpha dash were put into like the dimensions. You didn't put it.
Yeah, it's a scalar, therefore, because this is a scalar, therefore I didn't need an alpha prime for here because of the presence of these x's. I needed an alpha prime for dimensional analysis. But yeah, that's one. I didn't need an alpha prime because of that.
Okay. Just one more comment about what we were earlier saying. You see, we said that if we took a linearized fluctuation and it did obey the equation of motion, then that would be a problem. Now, a linearized fluctuation not obeying the equation of motion is an insertion of an operator whose weight is not 1, whose weight deviates from it. So, after the exponentiation, you see that if the Einstein equation was not obeyed, then the linearized fluctuation would be the addition of an operator to the Lagrangian whose weight deviates from 1, 1. Now, what's special about 1, 1? 1, 1 is a marginal operator. So, it's if you take a conformal field theory and add to it an operator that's not marginal, of course, that violates conformal infinity. So, you see that the connection between the problem at the vertex operator level will translate to a problem of being not conformal. So, you see already that you're going to see some beta functions. Right?
I didn't require phi of x was dimensionless. Isn't it just do x dot do x?
Was this phi of x?
Okay. No, thank you for coming. Thanks for.
Why is it do x dot do x?
It will be the trace part of the vertical line. That's the symmetric part, the 0 trace part, shouldn't that be the trace?
But you know, G and U is also treated as a dimension. So, you know, I worry about whether we should have put an alpha prime there. Probably. But see, phi of x is going to be normalized in the same way as G mu. And he's coming with dimensions from the point of view of space-time. And G mu, if you give x dimension of length, G mu should be a dimensionless field. Okay? So, just from the point of view of space-time, phi, G mu are all dimensionless fields. All the dimensions go into x. That's how it works. It's true that if you...
It is R2, right? R2 has
R2 has those.
No, R2 is worldsheet.
It is derivatives in metric.
So, two derivatives on the metric. Every term has two derivatives on the worldsheet.
Oh, right.
So, from worldsheet point of view, every term is dimensionless.
But it's the fact that R2 doesn't have any excess in it is very
That's the point. That's the point.
Okay.
Yeah. From the space-time point of view, now there are two different dimensions. There's worldsheet dimensions and space-time dimensions. Worldsheet dimension says everything is dimensionless. Otherwise, you don't have a hope of making a conformal invariant. Right? To every term is a two derivative action. Term in the action. Fine, no problem. Okay? But you're assigning x space-time dimension of length. That's why you need 1 over alpha prime to make it space-time dimensions. None of those objects have space-time dimensions. And therefore, there's no problem.
So now after this, the approach that we will usually that we'll take to compute the Weil anomalies here would be that of first computing a classical solution of the string propagating in some curved background, and then considering the small fluctuations around that classical propagation, which will give you which is something like classical solution for the worldsheet quantum field theory and some quantum fluctuations around those classical solutions. Okay, so for that I'll expand my X fields,
also known as the background field method.
the background covariant background field method. Yeah.
Just to put context, this is something anyone who's read Weinberg's book and looked at the computation of beta functions for QCD has seen this. One way of proceeding in order to compute effective actions is to compute the effective action in the presence of a background, is to compute the quantum effective action by expanding the action in the presence of a background alien, and crucially to set gauge that depends on that background. The gauge that you set in that situation is that the fluctuation fields obey d mu a mu is equal to 0, where d mu is the covariant derivative with the background put into it. Okay, and the background field method is a useful way of computing effective actions and beta functions.
So I'll use where x naught mu solves the x naught mu will be some classical solution for the worldsheet action that we have, and we'll treat these as quantum fluctuations. Okay. But in our treatment we want to maintain general covariance throughout the analysis, so that we don't stump. The results that we obtain at the end of the analysis are generally covariant and don't depend on certain choice of coordinate system in the space-time. Therefore, we need to develop a method to treat everything covariantly. And the problem comes from the fact that the pi mu is a difference of two coordinates. Therefore, it is not it does not transform like a vector. It's not a vector. Okay, so you need to write everything you need to develop new techniques to write everything in a generally covariant way. So for that we go to a different set of coordinate systems around x naught mu, which we will build by using the geodesics that connect the 2 points, which are x naught mu and x naught mu plus pi mu. Okay. And so if I consider a geodesic lambda mu t such that lambda mu of 0 is x naught mu and lambda mu of t is x naught mu plus pi mu. Okay, then this geodesic will obey the geodesic equation, which is lambda double dot plus lambda mu double dot plus gamma mu rho sigma lambda dot rho lambda dot this is rho sigma plus sigma. Okay.
So you mean lambda mu of 1 was x naught mu plus pi mu?
Oh, sorry. Okay. And
T is an affine parameter?
T is an affine parameter. T is an affine parameter from this. So
we're pretending everything's Euclidean, right?
everything is Euclidean.
So all space like.
Yes. So now we can just integrate this equation to write for an arbitrary affine parameter lambda mu t equals
and pi in this thing, is it infinitesimal or could we find it?
it is finite but small. Okay, and so I can write lambda mu of t as some Taylor series expansion around x naught mu, which is this.
Small compared to what?
Small compared to curvatures.
What is the expansion parameter in this case?
Expansion
I
parameter.
mean, pi mu if it's small, something like you're expanding the classical form.
Yeah.
Something like quantum fluctuation sound. I mean,
Curvature. That's it. Yeah. It's small compared to curvature.
okay, so should there be any factor of curvature? I don't know, like anything like 1 over something times pi mu.
Yeah, the derivatives will appear when once we write down. So there will be derivatives appearing of g mu nu when we do the expansion for g mu nu, and those terms will be like for the whole analysis to be valid. You would want that the pi mu be smaller than the length scales of curvature. In fact, even this analysis that you can build a coordinate system which along the geodesics, this can only be consistently done for a region much smaller than the curvature length scales, because you might always get into a geodesic. If you go to a large enough region, your geodesics may start crossing again. So, and you want a consistent coordinate system. So you're always in a very small region. Okay, so. And here the eta mu is the tangent vector at x naught. It's the tangent.
Unit normalized?
It's unit normalized, because that comes from the fact that we are working with an affine parameter.
And affine and actually length. The parameter is actually length.
Yes. So this is at x naught mu, such that if you flow along the geodesic made by this tangent vector at affine parameter 1, you will land up at this point.
Should it be pi naught pi mu by? Shouldn't it be pi mu?
This is pi mu.
So eta mu, if you want to flow along it for length 1 and then you come to.
So at t equals to 1, this whole thing will become.
Sorry, I think I misled you. If you are going to use eta in unit normalized, that fixes what your t is, then in general, lambda mu of some t will be x naught mu, but not necessarily 1. Because t is just the length along the geodesic from your point to the next point.
Yes.
And that need not be 1. So, I think you want lambda mu of t.
I want here lambda mu of t.
Not there. I'll really find you an arbitrary point.
I use an arbitrary point.
Then it will not always, because now I was thinking you were going to choose an arbitrary normalization for your affine parameter. But you've chosen a particular normalization for your affine parameter, which gives it a physical interpretation. It's the length from x naught to the point that you're interested in along your geodesic. Now, not every point is distance 1 away from you.
Yes.
So that will not be 1.
Or if I keep this one, then I can
Change the normalization.
Normalization of
You have to do one of it.
Yeah. So I'll choose to change the normalization of it.
Yes.
So okay. Now the reason I'm doing this, the advantage of coming to this coordinate system is the fact that.
So what is your just to be clear, what is your new coordinate system?
Yeah. So I'll be using the eta mu's as the new coordinates around x naught mu. Okay, and since we are following the geodesics in this new coordinate system, from the geodesic equation we can argue that lambda, all the gammas are 0.
Okay. Just to say this once again, what is being done? if you draw a picture, you've got a point in the middle, and you've got a region around that. Now, suppose I choose any other point. I want to find a nice geometrical coordinatization of that. So the question that you ask is, every point, okay, is reached from your standard point, starting with some geodesic. You make a congruence of geodesics. Okay, so you take, if you don't mind frontal and cross diagram, just to make it completely. Okay. I've got a point. Now, I start with all little arrows that I can around this point. These arrows are vectors in the tangent space around this point. That's clear? Now, let's take these arrows as the starting directions for geodesics. This gives me a set of geodesics that fill space. That's clear? So, every point is hit by some geodesic. Okay? So one way of giving coordinates to the point would be to say which geodesic and how far. That describes the point. Okay? Now he's got a slightly clever way. Firstly, he's going to, the geodesic, as we said, is labeled by the tangent to that point. So there are two things we could have done. We could have kept this tangent, unit normal. And then we would have to specify which geodesic, so which vector, and how far. What he is doing is to take that how far and multiply it by the tangent. Okay, so in way one, you would be specifying an eta mu which was normalized and a distance. What he is doing is something like Logar as it is fluid dynamics. So let me just call, it's convenient to just call this a new vector lambda tilde, which is tilde. Okay, that contains both pieces of information. The distance is the norm and the direction is the tangent. Clubbing these two things into it.
So it was necessary that you are in a small region.
What?
It was necessary that you are in a small region.
It was necessary that we are in a small region only so that the geodesics don't caustic. See, if we did this in flat space, we could do it forever. Because these are just radial lines that go out. It's just polar coordinates. Okay? In flat space, no problem. But in an arbitrarily curved space, you run the possible. So if you were on the sphere, for instance. Yeah, they come back. So, but that requires curvature. So as long as you're in a ball that's small compared to the size of the curvature, you're fine.
The expansion, you're going to put in the nth term there will be n etas and then they'll all be contracted with gammas, right?
Yes. And okay, I should also define what the further gammas would be. That's what you're asking.
No, I'm saying suppose you went to a local inertial field.
Yeah.
Then only the first term would survive.
Yes.
So their eta mu is pi mu.
Exactly. And then I'll go to, since I'm working with that coordinate system, if I had started with the clever choice of coordinate system, then my everything would have ended here. Okay. And is that amazing?
Sorry, just please say what you said again.
No. So what he was pointing out was that the fact that in this clever choice of coordinate system, since I am identifying this whole thing with pi mu, if I had chosen that flat coordinate system in that region to start with, then I wouldn't have these higher order terms.
So that will force the flat region to be infinitesimal.
Yes.
No, I mean, you're saying that in the coordinate system, eta mu. I mean, what? In an arbitrary coordinate system, you will get everything.
Everything.
Now, now you're going to a coordinate system eta mu, and I suppose if you were in that eta coordinate system,
at t equals 1, there will be only this term that survives, and all the other terms will not be there.
Why all the terms will not be?
Because it's a local inertial field.
What the derivatives of gammas will be?
Oh, the derivatives of gammas?
There are derivatives of gamma sitting out there, but at t equals to 1, all of that should cancel amongst it. Because that is because by construction you want that your eta mu should correspond to this particular choice of pi mu. Like if you are at this point and you you want to describe this point using this coordinate system. Okay, you have essentially mapped this point to. So if you have a tangent space at this point here, right? You have mapped every point in the vicinity of this point to some point in the tangent space. Okay, and if you are considering a particular point which always lies along this geodesic that maps to a straight line in the tangent space for different values of t. Okay, and from that picture you don't have any other higher order terms coming.
No, I think he's saying that if you go to the eta coordinate system, then by definition, in the eta coordinate system, the point that you get to is eta.
Oh, is it in a very particular coordinate system?
In a very particular
in a particular coordinate.
There would be a very particular.
Yeah.
Okay.
But this is not that. We are working with. So we are trying to use the information of the eta coordinate system to be able to write this in this pi mu in a covariant fashion.
Yeah. This is clear, right? It's just expanding how geodesics move.
And just the higher order terms, there will be derivatives of gamma appearing in the higher order term. So I will denote them by gamma mu, sigma 1, sigma 2, sigma 3, where these are just covariant derivatives like sigma 1 of gamma, sigma 1, sigma 1, sigma 2, sigma 3. Okay. Such that it is only it is covariant derivatives in only the lower indices. That's a detail that comes out when you try to expand this and go from this equation to this equation.
Right. And does everyone understand why there's that gamma times 2 times? Why the second term has gamma eta eta? Is that clear? The first term is clear, right? It's just first term of Taylor series expansion. Why is the second term of the Taylor series expansion there? Simply from that equation. Second term of the Taylor series expansion is a double derivative, but that equation tells you what the derivative in terms of. Now if you want a triple derivative, you take that equation and differentiate it. Okay? And you already know what gamma double dot is. So you iterate that. Okay? So this equation, the geodesic, all you're doing is integrating the geodesic equation in Taylor series expansion. So to start with, it moves in a straight line. And it starts curving this coordinates around. Okay?
Higher order of in the expansion, there will be lot of etas.
Yeah, and every subsequent order there will be one extension.
What will be the condition of the eta at t is equal to 1? I mean,
no, eta is defined at t equals 0. The etas are the tangents at the starting point. So in this clever choice of coordinates, since etas are essentially the coordinates in the tangent space of that can be defined as x naught mu at x naught mu. Okay, and this is a particular type of choice of coordinate system which is flat around in some region around x naught mu. I can, so if I was clever enough to start doing my analysis in that smart choice of coordinate system, what I would have got is this, that all my Christoffel symbols at x naught are 0. So let me denote that by some bar. So bar denotes that these are the Christoffel symbols computed in eta coordinate system. Okay, similarly, like all such covariantized objects, covariant derivatives of lower covariant derivatives on the sigmas, those also turn out to be 0, like symmetrized in lower indices. So these objects will also turn out to be 0. This is symmetrization in the lower limit. Okay, so this is important because now what I'll do is that in this smart choice of coordinate system, what I can do is, since I can use this information to replace the derivatives of the Christoffel symbols with R mu news, because R mu in this new coordinate system, Ricci tensor rho sigma is simply this. From which I can solve for this.
And sorry, you want to say a little bit more about why gammas were zero in this coordinate system?
See, the way I understand is because in this particular coordinate system we are always following the geodesic, so the deviation from the geodesic in this coordinate system is zero. Right. Therefore, as long as I'm at the point x0 mu, where this coordinate system is defined, and like I move to some other point in its vicinity along this geodesic, the geodesic equation simply becomes this: eta dot dot will be zero.
You say that we know that geodesics. Let me just read. And you say the geodesics eta dot dot is related to some Christoffel symbols.
Yeah.
You should also be able to just transform the metric. What we want to see is that the metric has no first derivatives. In etas, right?
It does, yes.
That the metric, when the metric as a function of etas starts out quadratically, that would be equivalent to saying that the first that the Christoffel symbols vanish. That if we take the metric and expand it around your section point x0,
Yes.
then it stops quadratically, right? Because if there are derivatives of metric, then there are Christoffel symbols.
One derivative, like one covariant derivative metric of is always zero, right? See?
Normal. Christoffel symbols are derivative of metric.
Right.
So I think basically what you want to say is that the metric is whatever it is. Linear terms in eta vanish, quadratic terms are non-zero. Quadratic terms are determinable.
That's something we'll be
You will.
checking. Yes, we'll be checking.
Yeah.
Okay. So, right. So I'll be using this information actually to, in a way, I'll be using this information to write down the expansion of any tensor around x0 mu in terms of this new coordinate system. Okay. So in this new coordinate system, if there is a tensor defined, which is mu1 to mu2, okay, at some point x0 plus theta, then I can write this as mu1 to mu m at x0 times theta mu1 to beta mu m, and the presence of usual derivatives here follows simply from the fact that the coordinate system around x0 mu, this particular coordinate system is a flat thing.
This is just Taylor expansion.
This is just
always
Taylor's
true.
expansion. Yeah.
Ordinary derivatives.
Yeah. And now what I would do is like replace these ordinary derivatives in terms of covariant derivatives and the Christoffel symbols and their derivatives. Okay, and using that, so there are similar relationships for higher order derivatives of Christoffel symbols. And using all those relationships, I can simply write this expansion, this Taylor expansion covariantly. Okay, so now if I replace all the del mu's in terms of del mu's and gamma Christoffel symbols, and then if I can in this particular choice of coordinate system, I can write all derivatives of Christoffel symbols, and Christoffel symbol is 0, all derivatives of Christoffel symbol in terms of the curvature. Then I can simply write a covariant form of this Taylor expansion,
Which then works in any coordinate.
Which works in any coordinate system, and then I'll use that expression to expand G mu nu here. Okay, in any coordinate system, and that expansion I'll be using to build a covariant formalism for the analysis.
To what order will you need to expand?
I'll be doing it as quadratic.
So the first derivative is just ordinary covariant derivative. The second derivative picks up one factor of a
Yes.
Is it possible to write out that formula?
Yeah. So I'll just write it down because we are interested in 2 tensor. I'll just write down the formula for the 2 tensor. For 2 tensor, it is this is the expansion for 2 tensor, and so now I can just replace these theta mu's with because this is a covariant equation. I can go to another coordinate system and use the same expansion for an arbitrary coordinate system. So I can use this expansion with my pi mu's, not worrying about and still being in a covariant representation.
But eta is still a special coordinate.
See, with the normal Taylor series,
But eta was pi.
after I've written this down, I have covariant as all the coefficients, and then this is just the that coordinate in that particular coordinate system. Now, if I move to another coordinate system, I can choose this to be any sequence.
But eta was pi.
So the same answer you would have got if you had just, you had the coordinate expansion at Taylor series.
Yes.
If you had just kept say first orders in derivative of gamma there and written down t bar minus, would you have got the same answer?
Sorry, can you come again?
You had a Taylor series for
Yes.
your lambda,
Yes.
right? And suppose I thought I'm expanding in 1 over curvature. So
Yes.
I kept the first derivative of gamma
Yes.
and drop our second derivative and here.
Yes.
Is it the same answer you would have got?
I guess so. That should have.
Wait. Yeah. Wait, what is the final? Just can you just state the final formula you're going to use? Are you going to use it? You're going to use it with, because you're going to say that eta is pi. You're going to replace eta with pi.
I'll use eta here, and I'll use the objects computed in pi coordinate systems.
So yeah, the objects were here already computed, but you're going to use eta as the fluctuation.
Eta is the fluctuation.
It wouldn't have been true for just an ordinary expansion because the gamma term would not have been there. The first gamma term. I mean, we are expanding in this very particular coordinate, which is the tangent of geodesics. The expansion coefficients are covariant derivatives in an arbitrary coordinate system. But the expansion parameter eta has a specific meaning. That's needed for this. You see, you should expect the coefficients of an ordinary Taylor expansion in coordinates to be covariant, because coordinate differences don't transform nicely. Right? So it's only in a nice expansion that you expect coordinate coefficients to be covariant, and that's what I see.
And you just to remind, the remark that eta mu's are nice here because they are in the tangent space. So you know they transform nicely under local the transformations around that.
Right. Yeah, coordinate difference is never nice because it's nice about what point. Which
So now my setup for writing a covariant means the techniques that I'll need to write a covariant expansion for this the action are like complete. So now I can just write an expansion for G mu nu using this particular expression and replace it here, and similarly do the expansion for the x.
So G mu nu is clear, and will you help us with the expansion for x?
Yes. So for x, now what I want to compute is this del alpha x naught mu plus pi mu. Okay, and if you recall, we had an expression for pi. We had written down the expression for pi mu, which was this eta mu minus half gamma mu some expansion which you had obtained from the Taylor, writing the Taylor series at equals 1. Okay, so I can just plug this in here, okay, and compute the derivatives. So this thing will become del alpha x naught mu plus del alpha eta mu plus del rho eta mu del alpha x not mu, and so on. Okay, and this quantity, because this quantity, because this I can identify with gamma mu rho lambda eta lambda.
Okay, so you're saying that x naught actually I didn't understand.
I had an expansion for pi mu's in terms of etas.
Yes.
Okay, I plug that in and just take the
which can you put arrows to which term is what?
This term will contribute to both of them.
Will contribute to both of them.
Because first you can differentiate this directly with respect to alpha.
Yeah.
And and the second term will be the one in which you take the derivative with respect to the x coordinate here. And then differentiate that to x coordinate.
Wait, so eta is a function of x, right?
Eta is a function of x.
And theta is a function of sigmas of the worldsheet coordinates only because it's a function of x.
Okay, that's true.
Second and third term should be same.
No, it's not necessary, right? You could take this phi, the fluctuation around x naught mu can be different around the different points on worldsheet.
Okay, so I see what you're saying. I see. That's a good point. It's a good point. You say eta is a function of pi. If you could write somewhere, eta is a function of what? How? Just what chain rule I use?
Eta pi is a function of.
I don't know. You're taking derivative.
So eta is a function of sigma and x.
What do you mean by sigma x? It's a function of x is what is x. It's not.
Yeah.
Eta is a function of sigma and x not sigma. This is what I'm trying to So,
This makes sense, right? For any classical solution, the fluctuations can be anything. So that's why it's a function of sigma. But then for different classical solutions, you'll have different ways. So it's also a function of x naught.
okay, sorry. Just 1 second. Theta is your tangent thing.
Yes.
So, and it's a label of points, where you are, how far you are.
But also depends on the classical solution.
Understand. So if this is my particular choice of classical solution,
That is outside the video.
so if I consider a particular, say this is my x naught, which is a solution of equations. Okay, and your eta is some fluctuation around a point here, right?
Yes.
So now your eta. So for a given classical solution, your fluctuation can be different on different points of the worldsheet.
Yeah. If you don't mind, could you just clear that part and just rewrite your data exponential? I'm sorry, it's probably not super.
I'm doing this. This acting on this is simple. Okay. Now I have del alpha acting on eta mu, which is a function of sigma, and x naught, which itself is a function of sigma.
done that in the class.
Okay, so now if I want to compute this quantity, so first will be the usual derivative just in terms of this coordinate. Okay, so that would be, that I am denoting by del alpha eta mu plus first I differentiate with respect to x naught mu, so that is del mu eta mu. Okay, and then I compute del of x nu which is
I'm still. I've got a well-sheet configuration with certain x naught
yes
and plus some fluctuation.
yes
At any given point, that fluctuation is something.
yes.
It's true that x naught is something, but also the fluctuation is something.
Mhm.
So why isn't it just derivative of the fluctuation?
You're saying this part is
See, at the level of pi mu,
ah,
would it be just del alpha of x naught mu plus del alpha of pi mu? Is that right?
yes. Oh, no. Del alpha, yes.
So this is del alpha of x naught mu plus del alpha of pi mu, right?
No, but pi mu also, even at this level, your pi mu is a fluctuation that depends on where you are, right, in the
On the worksheet, yes.
Yes.
So you take the derivative of that.
Yes.
Okay. Now you have a formula for pi mu in terms of your etas.
Yes.
And you're saying that formula knows a. This I'm still not understanding.
Oh, because see, now when you write pi mu's in terms of eta mu's, then your eta mu depends on the choice of eta mu, also dependent on x naught to start with. Like what point in your space time
But
are you at?
I can't use pi mu is equal to eta mu and just say therefore del pi is del eta. Just as numbers they're not equal. I'm sorry. But I'm not getting
So theta mu's dependence on x naught of sigma is clear. This special separate dependence of sigma is not becoming clear. Sigma comma x naught sigma.
Good. If you don't mind, I'll just ask. If you don't mind, I'll just start here.
Yeah.
So we have del alpha of x naught mu plus 1.
Yes.
This is equal to del alpha of x naught mu plus del alpha of pi mu. This is true.
Yeah.
Yeah, I'm going to put this way. This is not important. So we were interested in finding del alpha of pi mu.
Yes.
Okay. Now this is equal to del alpha. You said let's take the first order
Yes.
of eta mu. This eta mu, it's true that what it so what is this eta? Given a point pi, sorry, pi is eta. I'm sorry, you're probably right. Just next to it.
See, yeah, I think okay. The point is that if you went to a different point different x naught here, it is in the tangent space of x naught.
Right.
Right. So it is a fluctuation in the tangent space of x naught.
Right.
Since the fluctuation, as we saw here, depends on sigma, on the worldsheet coordinate, plus the fact that the tangent space itself is labeled by what point in the space time you are at.
Correct.
You need to take that
Correct.
two derivatives in terms of.
Correct. So you're saying the question of what is the change in eta is not even well defined because it's a vector in one vector space minus a vector in another vector space.
Right.
Okay, so you need some sort of connection between the two. You'll need a Christoffel system. Okay. Okay, please go on.
So precisely like that. So even if like at first order, this is what I want to compute.
Yeah.
Then the fact that this becomes eta mu, and now since I want to connect it also to the tangent space of the some adjacent point x naught mu, I have this del nu of the eta mu times del alpha of x mu.
Yeah. So you see the old. Please go and get your final answer.
Okay. And now since by this particular means my coordinate system, since it's special. Okay. I know that the del nu of eta, the way it's constructed, can be written same as this. The covariant derivative is not there, so it's just like this quantity, eta lambda nu.
If you just take the final answer
The final answer
from the first order term.
Del alpha eta mu plus mu
So the final answer is that you take this eta. So you've got an eta here and an eta there, but you want to take the difference. You first parallel transport it, this guy to this guy, and then take the difference.
Yes.
That's what you're saying is the final answer. And so this final answer makes a lot of sense, and nothing else would have been reasonable. And you're saying you have an algebraic way of getting this. That's still not entering my head, but I'll give you. Yes.
So I'll just define this quantity for brevity as this covariant derivative of eta mu, and now I know how to write this an expansion, and I know how to write this an expansion.
Del alpha eta mu is del alpha eta mu is del alpha eta mu plus gamma mu.
It's not the usual covariant derivative.
The usual one you have set to 0, right?
Yeah. I mean, this is not the usual. It's some notation. It's just the notation. This is the space-time thing. This will become just like in a minute. You will see this will become the covariant derivative on the worldsheet, where the local Lorentz symmetry, where this acts as the gauge field of the local Lorentz symmetry in x quantities.
Yeah. And the reason this is reasonable notation is because it is exactly what we said before. That what you're doing is taking the difference after a parallel transport in space-time. You see, because you've got two different points in space-time. At sigma, x naught is also different. Right? So you move from one sigma to another, you're moving from one x naught to another. Had those two x naughts been the same, then these two etas would have been etas in the same tangent space. But the two x naughts are not the same. So one eta is an eta in one tangent space, the other eta is an eta in another tangent space. You can't even subtract them. You can only subtract them after you parallel transport. Right? So this derivative is parallelly transporting and then subtracting.
That is covariant derivative.
It's covariant derivative in space-time, though this is a worldsheet derivative. You see, it's the difference between an eta here and an eta there. But that difference is taken as follows. This eta here is a vector in the tangent space of x naught of sigma. This eta here is a vector in the tangent space of x naught of sigma plus delta sigma. X naught of sigma plus delta sigma is a different point from x naught sigma. So you can't subtract these two. But you can subtract them after parallel transporting. Parallel transporting in space-time. And that's what this operation does. Okay, I still haven't actually quite got how algebraic. I mean, it's clear this is the only sensible thing that you could get. I still haven't actually got how algebraically. See, you had some algebraic steps that haven't entered my head, but I'll. Yeah.
Should I go through them or like?
I think it's fine.
We can go ahead because
yeah.
then.
Yeah.
Okay, so I'll just write
Don't have the last thing.
Yes.
this.
Yeah.
I mean, you already did that.
So because I needed, so I'll just write the expansion of this now using what I had, using the expansion that I had written earlier for G menu and the expansion we just developed for delta alpha. Okay, so
And that del x is del x naught.
sorry. X naught plus 5 is I'll just write the linear term also here, but linear order term will not be there because I'm looking at some classical solution. Okay. And so this term is not there, and it, yeah. And then there are so this is the expansion for the Polyakov part.
The first two were just from del x, and the second one was just from.
Yeah.
What about constants? One order from G, one order from G to X.
Oh, actually, if
You're keeping only quadratic.
no, he's asking for the terms that come from G mu not X and like order one term from this and order one term from this. So this term forms from various combinations.
No, but you're keeping only quadratic terms in eta.
Yeah. So I can do it. I could take that quadratic from here and 0 0 from here.
And there's nothing else you can take because G starts quadratic in eta.
Because of special coordinates.
Because, yeah.
And so before I write the expansion for this thing, I'll just write down. I would identify this as the propagator term and identify the correct propagator for. To identify the correct propagator, now I'll go to like fix my gauge, compute the propagator, and identify the objects, the gamma objects that appear here as the gauge fields in the worldsheet metric for the local Lorentz symmetry. Okay, so for that I would first introduce Weilbein formation formalism, in which I go to a locally flat like coordinate system by a transformation from eta mu to some eta I by Shiraz?
Yeah, please.
Okay, I'll do a coordinate transformation that
This
takes
is on the worldsheet on space.
this is on the space. Okay, so that then I can write the kinetic term as delta ij times L alpha eta I plus eta I comma E. This is the first thing, and similarly for delta this is and J and the merit of doing this is that I get a I can identify, so now from the worldsheet point of view, I can identify the propagator from this particular part, and I can view this quantity as the gauge field for Lorentz transformation, local Lorentz transformation, which is the symmetry for the. So from the worldsheet point of view, there is some symmetries in capital X, which are scalar fields in from the worldsheet point of view, and under that local symmetry, there should have been a gauge. There should have been a gauge field, which appears here. Okay, so now it is similar to the kinetic term for the Yang-Mills action. In the sense, this gives you a gauge field, matter field interaction, and gauge field matter field interaction. Two vertices like this and this.
What are the lines?
So these are the like etas, eta I, eta j, and this is this quantity that is I called omega, and these are omega, eta, eta. These are the two vertices, and the kinetic term becomes very simple. It's just 1 over p square. Okay. So I did this essentially to identify that there are terms like this, and to be able to compute the correct kinetic term in the worldsheet term. Okay, so which I can, since it is del alpha eta, del alpha del it's just the P1.
And you're going to treat those other eta things as interactions.
These things as interactions.
Along with the arcs.
Yeah. Although it won't contribute. I'll later argue why these terms won't contribute. So I'll just rub this area off, and right now I'll do the expansion for the antisymmetric part of the action. Okay. So the antisymmetric part of the.
We just need to know what B is. The rest you already know.
Yeah. There's a slight difference because now, while writing this, I had ignored the covariant derivative of G mu nu, but in the general expansion for T mu nu, we had a covariant derivative. So there'll be a different order term. Okay. this is again first order term which essentially if I am expanding a root till classical solution it won't be there, and then there is this. Despite the fact that it looks like doesn't say much.
So now we have pronouns crossed.
We have and that will actually be good here because you had pointed out in the previous class, there was an additional symmetry in this part of the action, which is B mu nu going to B mu nu plus lambda mu minus mu lambda. Okay, where this again in the power of x. Okay, and you want to be able to write down this part of the action in a way such that it is invariant under this symmetry. Okay, and for that, you define a free form which is simply h mu sigma is del mu beta mu sigma plus del, which is dv essentially. I am writing it in coordinates, but it's dv because this is a two-form field. So sigma mu plus del sigma v mu sigma. Okay, and I can just rub this off because I can package this whole thing nicely into. I'm sorry for first writing it and then rubbing it off, but this whole thing is simply h mu ij, where ij is now these ij's of the Wilben formalism that I it's not del alpha x not u I the curvature, I absorb the curvature in defining this, all the curvature terms in defining the derivative of.
Right, because you're saying that there were two gradients, because that's del and del. Because h is itself dv.
Yes.
And you say that because of that, by reordering gradients,
you can
get rid of a curvature.
So, right, so this is done, and there remains this last piece which I have to expand. And once that expansion is done, we can start with actually doing the while anomaly calculation. So now with all these, now once I have expanded the action covariantly in perturbation theory, I can go back and start compute whatever I want to do with this action. I am treating these as the fields, etas as the fields. Okay. On the for a worldsheet field theory. Okay, so okay. Now what I am interested in computing, since the whole reason I started doing this was to see that whether my field theory on the worldsheet remains while invariant after I introduce these position dependent fields, whether that is the case or not. So for that I would want to compute the while anomaly for this particular expanded action. Okay. Now and the what will I treat the perturbation in? There are essentially two length scales here. One is the length scale provided by alpha prime, and there is another length scale which is provided by the derivatives which appear in R menus. So the curvature of the space time, and similarly this is like a derivative term. So this and this. So this is two derivatives here and a one derivative here. Similar means I'm saying one derivative, or in this form it's a one derivative here and a two derivatives here. So I'll do a simultaneous expansion, derivative expansion, and the alpha prime. So
you never expand the R2 down in the
R2 is two dimensional. It's a worldsheet R. It is not capital H dependent. So to compute the while anomaly, what I am interested in computing is the trace of the worldsheet, like trace of worldsheet stress energy. Say this is worldsheet. Okay. I want to compute this quantity and check what is the condition for this to vanish in this particular field theory. Okay. So now to compute this, actually, so if you think about it, after this introduction of these particular fields, when you vary your scale, the while factor of your worldsheet metric, there is an additional term that might arise, that might add to your action. Okay, that's and that term is the anomalous term that arises due to variation of your while factor. Okay, now you could associate that term either with non-conservation of stress energy tensor, or you could associate that term with non-zero trace of stress energy tensor. and these two choices are equivalent because the term appears here as a scalar, and it's a matter of choice where you want to put that extra term while computing t mu views. Okay, so what we'll do is like we'll assume that the conservation of stress energy tensor holds and associate all that extra piece with the trace of stress energy tensor. So we'll assume that the conservation holds and the Weyl invariance does not. Okay, so therefore we'll use the conservation equation. So the conservation equation is this: P Z Z bar plus del Z bar P Z bar equals 0. Okay, so I will use this equation to compute T Z bar, which is same as trace of stress energy tensor. Okay, and I'll do this in momentum space. So this equation in momentum space becomes Q plus T minus plus Q minus T plus is 0.
Both of those are Z bars there. The second is
These both are bars. And this is Z. And there will be another equation. So this is minus plus. So I can maybe I should replace Z. So this is what I'm making. And so I will try to compute T plus plus in this particular field theory, and using this equation I'll relate it to T minus plus.
Lack of holomorphicity of T plus plus is related to the two. So that's that's like del Z bar of T Z. Right?
This is del Z bar of T. Yeah. Which yes. Okay. So I've reduced the problem to computation of T plus for this particular field theory. And now T plus has in this with this action has contribution from all three parts of the action. Okay, so one by one I will compute the expectation value of T plus first for the Polyakov part of the action, then the anticipated part of the action, and then the dilator part of the action. Okay, so for the Polyakov part. Okay, T plus is delta plus eta I, delta plus eta I. Okay, and I want to compute this expectation value. So the first Feynman diagram that contributes to this computation is the one with one insertion of T plus and one insertion of the first vertex, quadratic vertex that arose in our expansion of SP, which is this particular eta I, eta j.
And what about the other terms that were also there, the quadratic term and the kinetic term of eta?
the kinetic, so there was this gauge field term that comes from the kinetic term, that's true, and so there were these two diagrams, this diagram and this diagram. Okay, but based on symmetry, I know that these objects, these gauge fields are not symmetric under, are not covariant objects. So any insertion of these objects as an external line will not be will not give me a covariant answer.
You're saying they contribute zero?
They contribute zero.
If you did the calculation, you would find zero.
Yes. So even before doing the calculation, you could argue that the contribution is non-zero because you are looking at just the covariant results, and the contribution to covariant answer should not come from a non-covariant.
Yeah.
So now this diagram computation is not difficult. In assume insertion of q momentum here, this is p plus q and this is p. Okay, so this the loop integral is simply
Log divergent.
it looks log divergent, but I can get a finite answer by proper regular this plus and there will be an overall del alpha x del alpha x. This became r mu nu because while identifying the I and j becomes identified because and therefore this is phase level that gives you r.
Right.
So this integral can be computed.
Sorry, I lost it. Why the external gauge fields?
Because they are not covariant objects.
Covariant under what?
The space-time transformations. They were created out using gamma mu nu rho.
Gamma mu nu rho.
The Christopher symbol. So I just argued that any answer should come out to be by insertion of those objects should not contribute to your final.
And you could just check that by calculations.
I haven't.
I'm not saying that, but I mean, in principle, conceptual diagram, and you can just check with the
Yes.
diagram. When you have an expectation, which one to check?
Yes.
What about just the diagram which is a circle with a cross? Without any insertion on the right?
That's cancelled by the costs. That is the Weyl anomaly of the free theory.
I'll give you the final answer for this, which is 1/4 minus q plus by q times this. So this momentum integration after appropriate regularization gives you this.
Since there's no epsilon.
No.
Yeah.
In fact, it's not very difficult to do because you can go to polar coordinates and you can write e plus is e to the power minus I theta.
It's because there are pluses up.
Yeah.
Thank you. Yeah.
So therefore,
So q plus by q, what is that answer?
minus 1/4 q plus by q minus times this factor. And I know t minus plus expectation value is q minus times t plus plus divided by q plus plus. So finally t minus plus for Polyakov part is just minus 1 over 4 r mu nu del alpha x mu del alpha x mu. And so if I were working only with this part of the action, if I hadn't introduced these two extra terms, then for the Weyl anomaly to vanish, you would have required r mu nu to be equals to 0. Okay, and which is the same as Einstein equation for yeah. So this already points to us getting Einstein equation in some sense. So now I'll do the same thing for the antisymmetric part of the action. Okay, so for S it is antisymmetric. The only term there, so there are two diagrams that contribute. One is this, and the other diagram is this. Yeah, I should have written the Feynman rule somewhere because
It's fine. But why doesn't just a single insertion, single linear insertion?
The single linear insertion does not work because because of the antisymmetry of h mu ij. So if h mu, so let us just see that. So if there was a single insertion here, okay, this point, so there is an h mu ij that appears here.
I see. But you can't subtract this.
Yes. So that becomes
So it's clear you're getting h square structure.
h square structure.
Both diagrams you get h square structure.
Yeah. Okay, I think I should just write what the Feynman factor here is. So this particular thing is beta alpha beta h mu ij del alpha x mu eta I eta j. Okay, now if I contract this thing with itself, that makes I equals to j because this was eta I equals eta j. Okay, and but h is antisymmetric in ij, so the trace over ij and this is 0. Therefore, this does not work. So the evaluation of this involves exactly the same integrals that we did earlier, and the final answer just becomes this.
So you have three propagators now.
You have three propagators here, but the contractions are such that this propagator does not means the terms. Yes, they cancel amongst themselves to just give you exactly the same integral. And the final answer for t minus plus is minus 1 by okay, and this diagram gives a contribution which is we noticed that the second diagram gave me a structure which was different from the structure that I had got from the polyactive action, in that here, so okay, so this is which that it is antisymmetric in the alpha beta derivatives, while the first structure was traced over alpha beta. Okay, so and as we will see that it is, and the important point is that this is essentially the same sort of difference between this term in the action and this term in the action, where this appeared, d mu appeared with antisymmetric derivatives of alpha beta, and this appeared with traced over. I think I missed this sign.
And the cross always represents just the symbol thing.
The cross is the insertion of stress energy.
And the stress energy tensor itself is just del eta.
Yes.
You could also have contributions to the stress energy tensor from expanding those guys, but those could contribute
at a lower order. That will be correctly sub-reading order.
Yes.
So, and now this last piece of Dillard-on action remains. So, which is a little more trickier than in previous two computations. Now, okay, if the stress energy tensor, the contribution to the worldsheet stress energy tensor, in the presence of this particular term, is non-zero even if you are looking at flat worldsheet. So up till now, both these computations were around flat worldsheet. Now you will say that in the flat worldsheet R2 is 0 and this term should not contribute. Okay, but when you means it's the stress energy tensor, computation of stress energy, the stress energy tensor is essentially the trace of stress energy tensor is derivative of phi. So even when R2 is 0, there is a finite contribution to stress energy tensor coming from this term. And that is not surprising, because as soon as we wrote down this term, we realized that this was not Weyl invariant, and there was therefore no reason to assume that the trace of stress energy tensor even for R2 equals to 0 should be 0 coming from this term.
Then you get something like del square phi.
Del square phi. Yeah. So P alpha for Dillard term is del square box sigma. Where this sigma is to denote its own worldsheet. Phi of x. Okay. And this holds even when R2 is 0. Okay. So now I want
what is 0?
When the worldsheet is flat.
Yeah.
So as soon as you choose to include this term, okay, even when this term itself vanishes, there is a non-zero contribution to the trace of stress. Okay. So now I want to compute this quantity. Okay, and again, as we had done previously, we can do an expansion of this around x0. Okay, so that will give me that will simply give me this box x0 mu del mu phi of x0 plus del alpha x0 mu del del mu y. And this is like the first term is this is del alpha phi. So you first have the derivative of this thing, okay, which again comes from, there are two terms when you have the first derivative, because this depends on x, and so there is one term after first derivative, that is del alpha x del mu phi, okay, and the second derivative consequently gives you two terms. So once you have this, now you would want to substitute the solution for x. So this is classically means now since we have
the equation of motion.
we will use the equation of motion to replace this here and here. Okay, so using equation of motion in presence of both these two terms in the action is this. So I'll take this and replace it here, because I want to keep that space to list all the things. I'll just rub this off and write the final answer for T alpha alpha. So T alpha alpha data term is del mu phi plus phi del alpha x not mu del alpha x not mu minus half lambda phi x not h lambda So despite the fact that at this stage things look non-covariant, we see that after substituting equation of motion, this becomes a covariant derivative of phi. Okay, so this, so the full trace, I'll just read it. So the trace contribution to the trace coming from the Dirac part is simply 1 over 2 del mu del mu del. So the factor comes due to my stockiness in between in keeping the factors of inverse of metric and other things. So, this I have checked out. The final answers are given in notes for. So now we have the total trace of stress energy tensor is the sum of this part plus sum of this part plus sum of this part for this theory. Okay. So let us just think what have we done till now. So we started off in this course. We started off with doing the string theory on flat space-time with flat world sheet, and there was no stress and no trace. The theory was exactly bilateral. Okay. Then we introduced curvature in the world sheet metric, and we got a trace of stress energy tensor which was proportional to C times R. Okay, and we chose our host system appropriately so that this theory still remains valid. Now we have said that the metric is not my space-time is not flat, and we get a contribution to the trace of stress energy tensor due to the non-flatness of space-time. Okay, and which is the sum of this quantity. And we still need to check that what happens if we. But till now, when in all this computation, the world sheet was flat. So we essentially need to go and ask what happens that now if we consider a curved world sheet, then what happens?
Essentially, you've got the beta function, the G mu and B mu.
Yes.
Now we're going to try to get the beta function for phi.
Right. And that comes again. So that comes from the fact that's where the structure becomes important, because this again, when I computed the Taylor stress energy tensor, it was these two same structures that were appearing. Okay, so till now we have two types of structures, and they, as we will see, they go and correct the G mu nu here and B mu nu here, and what we will be computing next will go and correct this particular. Should I complete it?
How long? 10 minutes, I think. Let's finish. You're very near the end.
I am. If I don't go into the details, like if I do it.
Tell us the main idea.
Okay.
So next week's going to be NSM. I don't think we should have class then, and then such. Yeah.
Okay. So, the question that we are asking is that if we don't have a flat world sheet metric, then what is the contribution to this stress energy tensor? Okay, and the way we compute that is very similar to what we had done earlier in the course, which is to compute. So first we notice that this, with respect to phi, where this phi is linked, that was a capital phi, this is small phi. Small phi, sigma is the value factor of the metric. So I'll go to some metric which is e to the power phi x d alpha b, which I can always do locally for a two-dimensional version. Okay. And now, with respect to variation of this phi, how does t minus plus change is what we want to compute. Okay. We compute this, and this at phi equals 0 is simply the for the flat world sheet is simply the 2-point function of stress energy tensor. Okay, and I'll compute this 2-point function and do a functional integral to compute the t minus plus for a general case of for the general y factor phi x. Okay, and
you compute this just in flat space.
This is computed in flat space phi equals.
So then you will get it for small phi.
Yes. Yes.
And from there you will go it.
Yes. And this is very similar to what we had done earlier.
Because curvature is just del square phi.
Yes. Yes. Okay. So this.
Once again, you'll replace the t plus.
Once again, I'll replace it by t plus t plus. So I'll be computing the 2-point function of t plus tt, t sigma t0, and then I'll come to this and then do the integration.
And so just show us the diagrams.
Okay. So the diagrams that contribute from the first part. where this is the one with the R mu ij. Okay. Then there is from the anti-symmetric part. So this is the only diagram from the symmetric part, the Polyakov action. Then from the anti-symmetric part there are two diagrams. Where these are the H vertices that we had. Okay, and from the dilaton part, this you compute just this, where this is box x mu del mu phi del mu phi box mu. So by the computations of these diagrams, you can compute this quantity, and from there you can integrate to get t minus plus, which I can just write on the final answer.
Good. So these are the most complicated diagrams because of, for instance, that's a complicated diagram.
Yeah.
Cross.
Yeah. So the final answer is
So 3 by 6 is just 2 crosses.
Huh? This no. So this actually will cancel when you include the ghosts appropriately.
So that comes from the diagram with just 2 crosses.
This comes from yeah. Right. And with this inclusion, everywhere this term also appears. You'll just put a root g factor here and a g factor here to account for the fact that you are actually computing it with this part and you are not accounted for this. Okay, and once you compute this, so you can just write down, I'll just sum all these things together and bring all these terms with the similar type of structure together and write down the final answer for T million. Okay, I let me not do that. Let me just say that the sum of this structure plus sum of the same structure coming from here it should be equal to 0, and similarly, like all independent sum of all independent structures should come out to be 0. The symmetric structure, the trace structure, the anti-symmetric structure, and this R2 times root G structure. So for the theory to be Weil-Invariant,
maybe we could just say one more thing, which is that you see what you're showing is that a Weil transformation can be compensated for a change of the by a change of the original vector and the original mu and the original phi, because the effect of the Weil transformation is exactly like what you had in the classical action. You see, so you've got a Weil transformation, changing this with this term, let's say. Okay, but there was a term in the classical action that also had this term. Okay, so you could undo the effect of doing a Weil transformation by changing B mu nu in the classical action in a particular way. Okay? This is exactly basically a renormalization. Because a Weil factor is a change in scale. So what you computed, though you have to use those words, are the beta functions.
Beta.
For the flow of B mu nu, G mu nu, and phi. That's very beautiful.
I was going to say it in a slightly different way, which was the fact that I know that change of log z with the scale factor is exactly the sum of all these things, and you can just identify, take them to the other side and add to the G minus, B minus, and see these functions being as the beta functions for the G minus, B minus, and so when we club these terms together of similar structures, which we are calling, so the terms with the trace structure, I'll call G mu, beta function of G. With the antisymmetric structure, I'll call beta mu, beta function of B, and the trace structure, this structure, I'll call it as beta function of D. Okay, and so I'll write this, and this as sum of. So let me just. I had to return it somewhere. I've lost that thing because in this.
Let's say without factors. The first beta function of G, there's an R mu nu term, and there's an 8 square term, right?
And there's an 8 square term.
And is there also a del? Yeah, there's some del term, del mu phi.
Yeah, it is. Okay.
And just to say that the signs are such that if you've got positive curvature, you take a positively curved manifold, like let's say R mu nu, space-time was a sphere. The sign of the beta function is such that if you run to the IR, the sphere will become smaller and smaller and smaller. So RG flow of a curved manifold tends to shrink. Okay. So if you just had like curvature for a sphere, that could not be conformed because of the RG. But you could have curvature balancing against something, like an 8 square. And that gives you actually, when that sphere is chosen to be an S3, that gives you a SU2 SU2. There's a conformal point when this guy balances against this guy. I'm gone. Did you want to schematically write the other?
The B term would be some gradient of some gradient of H term. Okay, and then there is a contribution which comes from here, which is gradient of phi in H term. Okay, yes, and then this receives contribution only from the last stress and potential that we computed. I'll forget about this particular part because that is taken care by those. So we have alpha prime by 2 times that minus r plus h squared by 12 plus 4 del phi whole square. And actually after I remove the trace part here, I can trace this equation to replace r here and remove the trace part here, so that the final equations I can write in a form that are more easily identifiable, and there this quantity, this equation essentially becomes R mu nu.
So just to say, now you're actually writing a condition that something's 0. The original thing you wrote was the actual beta functions.
Yes.
So this
now is this is
beta function
equal to
0 implies that, is it?
Yes. So this equals to. Okay, so I can just put them in a form which is more illuminating. This one becomes del and this one becomes okay. So this is the same as the Einstein equation with some non-zero stress energy tensor. Okay, and these are two other constraint equations which can also be understood in some way, which I'll come to in a minute. The point is, in general,
Perhaps it'll be 15 minutes for lunch.
okay, sorry, just 2 minutes, last 2 minutes. Okay, in general, you cannot be sure that these set of equations have a consistent solution. Okay, but for this particular case, you know that there is a consistent solution because you can write down a classical action for which these equations come out as the equation of motion, and that action is essentially this. Okay, it is gravity coupled to scalar field and some flux. So this is the action that precisely gives you these as the equation of motion. So demanding that your string theory be the world sheet theory, world sheet string theory be while invariant, so that the whole picture makes sense, is consistent, gives you the constraint that gives you Einstein equation as a constraint of the theory. Like equation of it's a beta function equation which needs to be told, and that comes out from the Einstein-Hilbert action coupled to coupled to scalar field and a flux.
And the same action also reproduces the low energy S matrices
Right.
that we can independently compute. Fantastic. That was really great. Brief questions, comments.
So this last equation, is it something like a Liouville theory, like if you rewrite
Which equation?
the last equation that you have
This
written?
is space-time. 26 dimensions.
Also, we can take any 26-dimensional background just by appropriately choosing, say, for example, H.
We have to choose a 26-dimensional background to solve these equations. Okay, so you find the solution to this equation of motion, then you can use that. Notice one or two things, just one or two things. Maybe my next, this is really great. Okay, in the next lecture, though, unfortunately, that will be after NS, and I'll do a follow-up on this. Okay, I'll give you various ways of thinking about what branches, as explained to you, really beautiful. But one thing I want you to notice is that everything we did was in perturbation theory. Okay, perturbation theory of what? on the world sheet of the string, what was the effective coupling constant on the world sheet of the string? It was derivatives of the space-time fields in units of alpha prime. His loop expansion was controlled by this parameter. Another way of saying it was that his Newton's constant, his Planck's, his whatever, h bar was effectively alpha prime. So higher and higher orders will get you higher and higher orders of alpha prime, and therefore we'll have more and more derivatives by dimensional analysis. Okay, so this is the first order condition for Weyl invariance. Then there are corrections to this. Those will be corrections to the effective action of string. You generate alpha prime corrections, and so on and so on and so on. You can just keep going. Okay. All this so far we've been doing is still classical string theory. Okay, because we're just asking for the consistency of string theory viewed on the sphere. Okay, then there are new corrections to string theory from quantum loops of string theory. Okay, how to take that into account in this language is something that Ashok tried to explain to us in this quantum space time. Now, there was only some vague understanding of this before, speechless asking mechanism. The basic point is that you will have, there are new divergences that come from doing the integral over moduli space. And you can cancel those divergences by starting with an effective action that doesn't quite solve this, by starting with a configuration that doesn't quite solve the classical effect, the classical equation of motion. Okay? So, and that can be encoded into a quantum corrected effective action. Okay, so this whole story, whole structure, which Pranjal has very beautifully described the first part of. Yes. Okay, how clear were the technicalities? It's great. Okay, so we will treat this as more or less complete and beautifully done. Okay, thank you.